Welcome to another fabulous edition of Comet Algebra. This video is for Algebra 2 radicals. So we're going to extend our knowledge of radicals beyond square roots now into third, fourth, fifth, sixth roots. I'd like to start just by looking at a couple examples just to get your brains rolling back into the radical topic. So you already know the square root of 9 we write as plus minus 3 because it does have two answers. The third root of 27, we know that 3 times 3 times 3 is 27. However, this is not a plus minus. When there's a positive number under an odd root, then the answer is just positive. Here, when you're asked for the cube root of negative 27, then it would be negative 3, because negative 3 times itself 3 times is negative 27. Never an I involved when you have an odd root. Here, the fourth root of 81, since 3 times itself 4 times is 81, so this would be plus minus 3i. The fifth root of 243, well, 3 times itself 5 times is 243. And again, likewise, if you're asked for the negative. Sometimes your book will put a negative sign in front of a root, and then they don't want the plus minus, then they actually do want the negative root. So just a kind of a review there of where you'll run across negative signs. Now in this lesson, I'm trying to be really picky with the plus minus signs, and I noticed that your book does not always do that. So let's just kind of watch out for that in your book. So our notes start with a table here, and you will notice that this table is dealing with the real roots, where b is the number under the radical and n can be any root, even, odd. B could be positive, negative, or 0. And just again to please note, this is talking about reals and not imaginaries. So the first possibility on the table is that b is a positive number and the root is an even root. And then we know that it is plus minus. We have one positive answer and one negative answer. And here's a couple examples. The second possibility on this table on this side is when b is 0, and kind of Captain Obvious, if b is 0, it's going to have one answer, one root of 0. If the number under the radical is negative, remember this is talking about real answers. There are none. There are no real answers. And that's where we know the I, the imaginary, comes in. So on this side of the table, we are talking about odd exponents. So the first, when the number under the radical is positive and it's an odd root, we do have just one answer, and it's the positive root. Again, Captain Obvious, when we have a root of 0 at 0, there's one answer. And when the number under the radical is negative and it is an odd exponent, they just are looking for, of course, the odd root. So please just understand the possibilities from this table. Now let's look at some more examples. You could have a decimal number under root, and that's no problem. The square root of 0.16. Again, your book would just say 0.4, but I'm going to try to be strict about the plus minus sign. Here, when you have the third root, when there's a fraction under any root, I won't always write this step out, but I want you to understand that you can split the numerator and denominator and write it this way, and sometimes that helps us, especially if we have to rationalize or something. But in this case, these are both perfect cubes. Cube root 27 is 3, cube root 8 is 2, and notice no plus minus sign. In the same way that we were looking for squares, perfect squares, when we were doing a square root, now when we have a cube root, we have to start looking for cubes. And it's just different. It's kind of a shift with your mind. So I'm going to be very obvious about writing perfect cubes, and you will not do this later after you start seeing it. 8 happens to be a perfect cube. It is 2 to the third power. Obviously, x to the third is a perfect cube. And any exponent that divides by your root is a perfect root for that particular one. So since 12 divides by 3, I know that 12 to the third is a perfect cube, And so I'm going to write that as y to the fourth raised to the third power. So what I have here is this is a perfect cube, this is a perfect cube, and this is a perfect cube. So there's not going to be anything left under the radical. So we will just, doing the cube root of all these, we will have 2xy to the fourth, and again, no plus minus sign. Next example, we have a square root. So again, we shift our brains and we're looking for squares. We can probably see that 18 has a perfect square of 9 in it, and there's going to be a 2 left over. Now looking at this x to the 6th, because it divides by 2, x to the 6th is a perfect square. And it may not look like it because 6 isn't a perfect square, but any even exponent, since it divides by 2, can be written as that variable with the exponent squared. All right, y to the 7th is not a perfect square. So we kind of go back down to the closest even number, and I can break this up into y to the 6th times y, and that'll give me my y to the 7th, because y to the 6th is a perfect square. So I'm going to write this as y cubed squared. There's my perfect square, and we have this y is left over. So now I'm going to underline the perfect squares, so we'll see what's coming out and what needs to stay under the radical. Square root 9 is 3. The 2 will stay. Square root here is x to the third. Square root here is y to the third. And then what stays under the radical is a 2y. And now it's simplified. All right, now we're going to bump it up a notch, and we are going to look at a fourth root. Not many people recognize fourth root. I certainly don't. So when I'm looking at 162, I simply cannot tell. So going back to the old factor trees, they will never let you down, and you will clearly be able to see if there is a fourth root in there. So I'm going to do the factor tree of 162 off to the side here. Now looking at the factor tree, fourth root would of course be 4 of the same prime numbers, and I'm going to circle a fourth root that I see here because we happen to have 4 3's. So we're going to rewrite this 162 as 3 to the 4th times 2. So now looking at this a to the 16th, 16 does divide evenly by 4, so we know it's a perfect fourth, and I'm going to be very obvious still. I'm going to write it as a to the 4th to the 4th. So y to the 10th, not a perfect fourth, so I go down, start going down in exponents. 9 doesn't divide by 4, however 8 does. So we're going to split this y to the 10th into y to the 8th times y squared. Because y to the 8th is a perfect fourth, in fact it's y squared to the 4th, and there is going to be a y squared left over. Now I didn't put this in, but all of this is still under that fourth radical. So again, I'm going to underline the perfect roots that I have found. There's a perfect fourth there, there, and there. So pulling out the 3, pulling out the a to the 4th, and the y squared, and then what remains under the fourth radical here is a 2 and a y squared. And now it is simplified. All right, that should be the information you need to have a great time with this totally radical section of Chapter 6. Have fun.